Okay, so good evening, everyone. Um, I hope all of you can hear me and also that my slides are visible. It'll be great if someone could just confirm this on chat. Okay, thank you very much. Okay, so let us begin. So, well, I'm pretty sure that the exam was quite easy because people have done very well, but I don't want to talk about the exam today. Let's just get on with our class. Uh, yeah. So, with lecture 7 we finished the first half of our course. So if you recall, um, then in the first lecture I had said that I had roughly divided this course in two halves. In the first half I had mentioned that we will see how to solve differential equations, second order differential equations which involve functions in one variable, and now we are headed towards um, the main part of our course, which is to solve differential equations involving functions of two variables. So today's lecture is like a preliminary lecture, and the real action will start in the next lecture. Okay, so let's begin. So we are going to begin with some eigenvalue problems. So let me explain to you first what this what it means when we use the term eigenvalue problems. Like, what kind of problems are we talking about? So the motivation for this is to develop Fourier series representations of functions that will be used to solve PDEs considered later. So we are already familiar with different kinds of Fourier series. We have already uh, seen the theme in which they fit. There is always going to be some sort of a norm inner product space, and we will have a set of orthogonal functions which do not form a basis for that inner product space, but they form a normed basis. In any case, we will see that once again, and we will see another such instance today. We have already seen Fourier Legendre series on. We have already seen for functions in L2 minus 1 comma 1 the Fourier Legendre series, and for functions on the space 0 1, that is what we did in the previous lecture. We put an inner product on this and we looked at the Fourier Bessel series for functions on this interval 0 1. So let's see what we will do today. So consider the following boundary value problems where lambda is in R and L is strictly greater than 0. So uh, here lambda is, we are looking for lambdas in R, and L is fixed. L is a fixed quantity, fixed. And lambda is one of the things we have to solve for, one of the quantities we have to solve for. So L will usually be 1 or pi or something like that. Okay, so let's go ahead. So the first problem is we need to find, yeah, we have to solve this equation, y double prime plus lambda y equal to 0. And we need that y of 0, y is this function y, it is 0 at 0 and also at L. So y has to be a function, y has to be a function from 0L to the real numbers. Okay. And the second problem is also similar. Here we need y double prime plus lambda y is equal to 0. And the derivative of y prime at 0 and L has to be 0. The third problem is y double prime plus lambda y equal to 0. And y of 0 is 0. And y prime, the derivative of y at L is 0. And the fourth problem is y double prime plus lambda y equal to 0. Y prime at 0 is 0 and y of L is 0. And there's a fifth one. Here what we need is y double prime plus lambda y is equal to 0 and y of minus L. So here y is from, in the fifth one, y is a function from minus L comma L to the real numbers. So here what we need is that y of minus L should be equal to y of L, and the derivative should have the same property. Okay. The boundary condition in problem 5 is called the periodic boundary condition. So that's essentially because, yeah, I mean, as we will see quickly, immediately, that solutions of problem 5 are simply periodic functions with period 2 pi. I'm sorry, 2L. Okay, so let's just stare at these questions for a few seconds. And let me just repeat what I said. We need to solve for lambda and functions y which satisfy this. Okay, that's exactly what I've explained in the next slide, I think. So let's go ahead. So questions. Let us fix any one of the above problems. Say problem 1. So what is problem 1? Y double prime plus lambda y is equal to 0, and y is 0 at 0 and L. And y is a function from let's just recall this once again. In problem 1, y is a function from 0L to the real line. Okay. So for what values of lambda does problem 1 have a non-trivial solution? So if it has a solution, what are the solutions for that particular lambda? Any lambda for which problem 1 has a non-trivial solution is called an eigenvalue of problem 1. And given an eigenvalue, if we take the space of all functions which satisfy the problem with respect to this eigenvalue, then it is a trivial check that this space forms a vector space. Okay. I mean, yeah. So suppose we have, let's recall problem 1 is y double prime plus lambda y is equal to 0. Suppose we have two functions y1 and y2 which satisfy these conditions, y1 and y2. So lambda is fixed. So we are assuming that I'm sorry, this is y1 and this is also y1. Sorry. So y1 is one solution for a fixed lambda. So let's call that lambda lambda naught. And y2 is also a solution. So y2 double prime plus lambda naught y2 is equal to 0. And y2, right? Then it's obvious that uh, any linear combination of y1 and y2 is also going to be a solution. Okay. So therefore, yeah, non-zero solutions for an eigenvalue lambda are called lambda eigenfunctions, or eigenfunctions associated with lambda, or sometimes we also call it the lambda eigenspace. So by eigenspace, we mean it's a space of functions which uh, satisfy that equation with respect to lambda. So I hope this is clear. So problems 1 to 5 are called eigenvalue problems, and solving an eigenvalue problem means finding all its eigenvalues. So finding all possible lambdas for which this equation, I mean, this problem has a non-trivial solution. Obviously, we are not interested in the zero solution. We want to find out when it has some interesting non-zero solutions. And so finding all those eigenvalues, and secondly, for each eigenvalue, what is the eigenspace of solutions? Okay, so let's go ahead. So let's prove a very simple result. So problems 1 to 5 have no negative eigenvalues. Lambda equal to 0 is an eigenvalue of problems 2 and 5 with associated eigenfunctions y naught equal to 1. So, or in other words, y naught is constant. And lambda equal to 0 is not an eigenvalue of problems 1, 3, and 4. Uh, okay, so let's just see all these are very easy to prove. So let's just look at the first one. Let us prove the first two. The third is left as an exercise. In fact, even yeah, okay. So let's look at how is y0 is so let's look at problem 2. So I'm just saying that if we take this question, if we take problem 2, then if we put lambda equal to 0, then the constant function y0 is equal to 1. That constant function satisfies is a solution to this problem too. I hope that's clear. I mean, that's obvious, right? So yeah. So instead of y0 equal to 1, I mean, as we already saw that the eigenspaces are vector spaces. So I mean, I could have just said y0 equal to constant. So that's what I meant. Okay, so let's go ahead. Yeah, I mean, the proof is really trivial. So suppose lambda strictly less than 0 is an eigenvalue. So let's just okay. So let us write lambda is equal to minus a square. So a is positive over here, right? Because we are assuming lambda is strictly less than 0. So we rewrite this differential equation as, yeah, so what did we have? We have y double prime minus a square y equal to 0. So we just rewrite it like this. Okay. So the general solution to this is something which you would have learned in your uh, MA 108 course, right? So there are we find two linearly independent solutions. That's e to the ax and e to the minus ax, and any other solution is going to be a linear combination of these two. So this is the general solution. And plus we have these two conditions that y of 0 is 0 and y of L is 0. So when we plug in these conditions, when we put x equal to 0, we get that c plus d is 0. And when we put x equal to L, we get that c times, yeah, this condition, e to the al plus d times, yeah. And one trivially checks that this forces c equal to d equal to 0, right? So which means that, yeah, so which means that there are no non-trivial solutions. So in other words, there are no negative eigenvalues. So the only solution, if lambda, yeah, I hope that's clear, right? So that's not interesting when lambda is strictly less than 0. That case is not interesting. Okay. So in problem 2 we have, so this is also very similar. So so till this much the analysis is same till here, right? For problem 2, for all, in fact for all problems, only the boundary condition keeps changing, right? So once again, in problem 2 we have this condition y dash 0 is equal to 0, y dash L is equal to L. So why, when we put y dash 0 is equal to y dash L equal to 0, we get these two conditions, AC minus AD equal to 0 and AC this thing. And once again, since A is not equal to 0, this forces that C equal to D equal to 0, right? So you can, I suppose, okay, I have done problem 3 also. So in problem 3, we have the boundary condition y equal to 0, y dash L equal to 0. And yeah, so similarly do the other problems, right? So in all these cases, I mean, our solution has to be of this type, y of x equal to C times e to the power ax plus d times e to the power minus ax. And then we have to take a general function of this type and see when it satisfies and the boundary condition. And in all cases, we will see that the only solution is a zero function. Okay. So let's consider the second statement. So what is the second statement? It says that lambda equal to 0 is an eigenfunction of problems 2 and 5 with associated eigenfunctions, the constants. So let's see. So if lambda equal to 0, then the differential equation, it becomes y double prime. So it's y double prime plus lambda y is equal to 0. If lambda is equal to 0, then the differential equation becomes y double prime is 0, which means it has to be of the form y of x is equal to ax plus b. So in problem 2, we have the derivative y dash 0 is equal to y dash L equal to 0. And from this, we get a equal to 0 because y dash is just a. and thus y of x is constant is the solution in this case. In problem 5, we have y of minus L is equal to y of L. So, yeah, so in this case also, y of x is equal to. So really there's nothing in this theorem. It's really trivial. So let's go ahead. So the upshot is that the only eigen values are lambda greater than or equal to 0. Okay, so now let's analyze this problem. So let's see. So the eigenvalue problem y double prime plus lambda y equal to 0, and with boundary conditions y of 0 is equal to 0, y of L is equal to 0, has infinitely many positive eigenvalues. So these are exactly the eigenvalues. And with associated eigenfunctions, yn is equal to sine n pi x by L. There are no other eigenvalues. So for each of these eigenvalue, right, the space of eigenfunctions is one dimensional, right? In general, maybe we could have had some eigenvalue problem, and uh, there could be some lambda naught y equal to 0, and then the boundary conditions, and in general the space could be more than one dimensional. I mean, there's no, yeah. So but in this case it turns out that the space of solutions is one dimensional. So let's see why that is true. So any eigenvalue must be positive by the previous theorem. So if y of x is a solution of y double prime plus lambda y equal to 0 with lambda positive, then we know that the general solution looks like this. Y of x is equal to some linear combination of cos root lambda x and sine root lambda x. Once again, this is from your MA 108 course. So now we just put in the boundary conditions and see what happens. So y of 0 is equal to 0 implies c1 is equal to 0. Yeah, that's obvious because this term is just going to vanish when we put 0, and this term is going to be 1, so we just get c1, and that is 0. And so this implies y of x is equal to c2 times root lambda x, and we want c2 to be non-zero because otherwise we are not looking for the trivial solution. And y of L is equal to 0 implies sine root lambda L is 0. This implies that root lambda has to be n pi for some integer n, right? For some integer n, right? This implies that lambda is equal to n square pi square by L square, and the only possible function then is sine n pi x by L. So in this example, the space of eigenfunctions is one dimensional. Yeah. So these are exactly all the eigenvalues. So n equal to 0, 1, 2, and so on. And we don't need to take the negative ones. Oh, right. So okay, I'm a little bit confused over here because so yeah, so there's a small check which needs to be done, because a priori, I mean, we could take a lambda n, and then we could have the two functions sine. Oh, okay, but of course sine minus n pi x by L is of course equal to minus sine n pi x by L, right? So indeed there's nothing to worry about. Yeah, sorry. So yeah, uh, so these two are of course linear combinations of each other, so therefore we just need to take all the, and we can assume that n is greater than or equal to 0. Right, I hope my doubt was clear, because for a minute I got confused that so n can be any integer, but n square will always, so all the values of The only possible values of lambda n are for n equal to 0, 1, 2, and so on, the distinct ones, because even if we take the negative ones, we will get the same ones. But then for each of these, we could have sine n pi x and sine minus n pi x, right? Someone has said should be written that any eigenvalue is non-negative. I mean, zero is not going to happen, right? Okay, so yeah, I'm sorry. Yeah, it has to be. I should. Yeah, no. Any eigenvalue must be positive. So yeah. So I should. What I've written here is wrong. Yeah, we cannot have zero because then we will just get the zero function, and we are not interested in that. So I'm sorry about this. Right. So yeah. So a priori, I mean, uh, a priori, we have both these, but of course, this is equal to minus sine n pi x by L, right? So we just need to take this one. So the space of eigenfunctions is one dimensional. Okay. Someone has written sine n star, yeah, is a linear combination of cos and sine functions. So it should be two dimensional. I'm sorry, I don't understand this question. I mean, the point here is that if we fix n, so we can take any n equal to 1, 2, dot, dot, dot. And then for this n, yeah, so for this n, the solution is going to be, for this n, the solution is going to be sine root lambda x. And that's just going to be equal to sine n pi x by L. How are we talking about dimension of solutions here? So that is what I explained earlier. So we had already observed, so let me remove this, right? We had already observed that when we look at this differential equation along with this boundary condition, right? I don't know, maybe you came late, whoever has asked this question. If we take two solutions, y1 and y2, if we take two functions y1 and y2 which satisfy, which are solutions to this problem, then y1 plus all linear combinations of these two also satisfy this problem. Therefore it is a vector space of functions, and therefore we can talk about the dimension of that vector space and stuff like that. Okay. Yes, I did say that the space of eigenfunctions for any lambda n is one dimensional. Okay, so let me go ahead now. Uh, and the second one is also very similar. We, in this case, we look at the second eigenvalue problem. So this is y double prime plus lambda y equal to 0, y dash is equal to 0, y dash L is equal to 0, has eigenvalue lambda naught equal to 0 with eigenfunction y naught equal to 1. So this is just the constants, and infinitely many positive eigenvalues. Lambda n is n square pi square by L square with associated eigenfunctions cos n pi x by L. There are no other eigenvalues. So once again, proof is okay. So I have left this as an exercise similar to the proof problem 1, and hence is left as an exercise, right? So okay, so let's look at the third one. So here the eigenvalue problem, y double prime plus lambda y equal to 0. Okay, maybe I should just pause at this slide for a few seconds and give you people a chance to think. Okay, so let's go to the next one. So now we are looking at the third one. So here we have y of 0 is equal to 0 and y prime L is equal to 0. This has infinitely many positive eigenvalues. So the eigenvalues are these with associated eigenfunctions, these. Okay, so uh, okay, yeah, no, this is fine. Yeah, there are no other eigenvalues. So okay, so once again, let's see how to prove this. It's absolutely same. The basic strategy. So any eigenvalue must be positive by the previous theorem. If y, uh, oh, okay, so this sentence is not correct. The previous theorem only tells us that it should be non-negative. So yeah, I guess that that's something earlier which the person was trying to point out. Yeah, so here I should strike out. I mean, the theorem only tells us that non-negative, right? But I guess in this case we can rule out if we have lambda equal to 0, then what do we have? We have y of x is equal to ax plus b, and we need that y of 0 is equal to 0, which means b is equal to 0, and we have y dash of L is equal to 0. But y dash at L is A. So this implies A is equal to 0, right? So that's not interesting. So it has to be positive. So yeah, uh, right. So all these problems will have a similar, very easy analysis. So here we take the general solution. So yeah, so now we can assume that y is, I'm sorry, lambda is positive, and we take the general solution. It has to be of this type, and we just y of 0 is 0 implies c1 is 0. This implies y of x is c2 of root lambda x with c2 non-zero, and y dash L is 0. It means that we need this. So root lambda into cos root lambda L is 0. So this implies root lambda L is equal to 2n plus 1 by 2 times pi. So it is an odd multiple of pi, right? So therefore lambda has to be this thing, is an eigenvalue, and the associated eigenfunctions are exactly these. So I suggest to all of you, this is like very easy, but if you find this interesting, then you can go back and revise it. And first you can, yeah, I mean, we've already all, yeah. First you can find the eigenvalues and then convince yourself that, okay, uh, the all the eigen functions are scalar multiples of this one, the one we have written. Okay, so let's go ahead. 4 and 5 left as exercise. Okay, great. Yeah. Okay. So note that in eigenvalue problem 5, every positive eigenvalue has a two-dimensional space of associated eigenfunctions. So eigenvalue problem 5 is different, slightly different, because let's recall what it was. So what we needed was y double prime plus lambda y equal to 0, and y of minus L is equal to y of L, and y dash of minus L is equal to y dash of L. Right? But as soon as we have this and uh, lambda is positive, so what do we have then? Right, you can check that if lambda equal to 0, we will only get the constant functions. And if lambda is positive, then we will get, yeah, so we will get cos, sorry. So the solutions will, our general solution will be y of x is equal to uh, c1 cos root lambda x plus c2 sine root lambda x. Right, and this function, so yeah, right. So I'll leave it to you as an exercise to, yeah. So you will have to once again get that all the eigenvalues are going to be, the eigenvalues are going to be n pi. Yeah, I'm not sure what the, yeah. So I don't know the answer now, but what the eigenvalues are going to be, but you will be able to find this easily. But the point is that these functions are already periodic. So once you have the eigenvalues, the space of solutions will be two-dimensional, because you can just take any linear combination of those. Right. So for instance, yeah, this is going to be an easy exercise, so I don't want to do it right now. So for instance, you could just take cos C1 cos n pi x by L plus C2 sine n pi x by L, right? So here the root lambda is this thing, right? And the space of solutions is therefore any linear combination of these two functions. Yeah. So there is a question, number of dimensions equal number of parameters. I don't want to use this kind of informal language, because I have already repeated twice very precisely what it means. When we take the space of solutions, that is going to be a vector space, and we are just looking at the dimension of the vector space. So here the space of solutions, any solution has to be of this type. So here, when let's say when I take, yeah, when I take, in this case, whatever your root lambda is going to be something. So I leave it to you to figure it out. But this will also be, yeah, easy. Okay, so let's go ahead. Uh, so once again, we come to our inner product spaces L2. So we say two integrable functions f and g are orthogonal on an interval a comma b if the integral of a to b f of x times g of x dx is 0. So more generally, so it should be immediate to you now as soon as you see this definition, that we are looking at the space L2 a comma b, right? So this space is almost like, for the purpose of our course, and yeah, for all practical purposes, this is the space of all functions uh, f in on a comma b, such that integral a to b f of x whole square dx is strictly is finite. And on these functions, we defined an inner product f comma g to be equal to. So this is exactly the inner product, right? So this is the first thing which should come to your mind. So right. So more generally, we say that functions, if we have a collection of functions, they are orthogonal if they are pairwise orthogonal. This is something which we have seen many times now. We have already seen orthogonality of Legendre functions, and in the previous lecture, we saw the orthogonality of the scaled Bessel functions. But of course, there inner the inner product was slightly different. There was a factor of x. So we will study Fourier series with respect to different orthogonal systems. Okay, so let me just, okay, exercise. So let's just look at all these functions, right? Right. So these are the eigenfunctions. So these are eigenfunctions in problem 1. Okay. So this is the eigenfunction for one particular value of lambda. This is the eigenfunction for another particular value of lambda, and so on, right? So these are the eigenfunctions for problem 2. These are the eigenfunctions of problem 3. These are the eigenfunctions of problem 4. These are the eigenfunctions of problem 5. Here, this is the eigenfunction corresponding to lambda equal to 0. So this eigenspace, the eigenspace corresponding to lambda equal to 0 is one dimensional. And for the other eigenvalues, they are all two dimensional. Yeah. Yeah, okay, I don't, yeah. So you have to compute lambda, right? So all these are going to be a basis for the eigenspaces, right? And so the exercise here is that all these are orthogonal to each other. So these ones, right? So from 1 to 4, the ones from 1 to 4, we will treat them as elements of L201. L20L, sorry, not 01. So we are looking at the normed linear space L20 comma L, right? So we are looking at this interval 0 to L, and we are treating these as functions. So we can, so the exercise is, take any two members of this set and view them as elements of L20L, then the inner product is going to be 0. Similarly, take any two elements in this set and treat them as functions on 0L, then they are going to be orthogonal to each other, and so on. And in the last one, in the fifth one, we have to view them as elements of L2 minus L comma L. I hope this is clear. So for instance, you will have to uh, pick up any two members here and then integrate them from 0 to L, multiply them and integrate them, and you have to show that this is 0. And in the last one, the exercises, pick up any two distinct members here, integrate from minus L to L, their product, and you will get 0. Okay. So we will study series expansions in terms of eigenfunctions, and it is used to solve PDEs. So for this, we consider the vector space of functions on the interval a, b, and define an inner product on it. So the inner product is defined to be this. So we denote by L2AB the subspace of those functions satisfying inner product of f with f is finite. To say that this is a comment which I had made long time ago. So when we take the space of all functions on AB, that is obviously a vector space. And to say that these functions uh, whose inner product with itself is finite, that there's a subspace, we need to check that if f and g belong to L2AB, then all their scalar multiples belong to L2AB. So we assume this fact. It should not be very hard to prove. But anyway, we won't bother about that. So from now on, we will always be working with functions in some inner product space of the type L2AB. In such a space, I mean, not even of the type L2AB, we will only be concerned with L2 0L or L2 minus L comma L. In such a space, the norm of function is defined to be norm of f to be the square root of f comma f. Okay, so let's go ahead. So Fourier series. So this is our first theorem. This is something which we are familiar with, or we have uh, seen similar theorems before. So we'd pick up any function f in L2 minus L comma L, and out of this f, we cook up a series. So I denote the series by f, capital F sub f here, this one. So I'll call it the Fourier series of f. Oops, sorry. Right? And this is defined to be a0 plus summation n equal to 1 to infinity an cos n pi x plus bn sin n pi x. And I will tell you how to get these numbers a0, ans, and bns. This is exactly like we did in the Fourier Legendre case or the Fourier Bessel case. But this is called the Fourier series of f on minus L comma L. So here a0 is 1 upon 2L minus L comma L f of x dx. And for n strictly greater than 0, so this is my a0, this is a0, and for n strictly less than 0, greater than 0, not strictly less than 0. For strictly, we define an to be this and bn to be this. And both all these numbers, so a0 is just going to be the integral of minus L to L f of x dx. Oh, I'm sorry. I should put a 1 upon 2L, is it? Yeah. And okay. Oh, okay. Sorry. What I wanted to say was a0. So a0 is, as we had seen earlier, it's just going to be the inner product of the constant function f itself divided by 1 comma 1. This is what I wanted to say. Right? If you remember, or in all, every time we wanted to write a series, right? So, and whatever, ans is going to be the inner product of this function cos n pi x by L f of x divided by the inner product of that function with itself. N pi x, sorry. Cos n pi x by L, right? So when you evaluate this, you will exactly get this expression. But I've just written it directly. Okay. So the above series converges to f in the L2 norm. That is, when we take the partial sums uh, and let n tend to 0, then the norm of f minus this partial sum. So if we call this Snx, this function Snx, so the norm of f minus Snx, it tends to 0. So I assume that you should all be very familiar with this, or at least this pattern, because we have seen this again and again in this course. So let's go ahead. The above means that the function defined by the series, uh, the Fourier series, is equal to f in a reasonably strong sense. We started with a function f of x and cooked up a sequence of numbers a_n's and b_n's, right? So, uh, yeah. So if suppose we knew that f of x is like this, yeah, yeah. So what I'm trying to say is, remember that in our what we had seen was, if we have this, if we have an expression like this, then we can get ai is as by taking the inner product, and that's what I was trying to explain in the previous slide. So maybe I should not write x, right? Ai is phi I divided by phi I comma phi I. Right. Uh, so the theorem, yeah. So we started with the function and we cooked up this sequence of numbers a_n's and b_n's, and using these numbers we cooked up another function, a series. And although this series is equal to f of x in a reasonably strong sense, it may not be equal to f of x pointwise. This is a theme which we have encountered again and again. And we now make some remarks about when the series will be equal to f of x pointwise. So this is the pointwise convergence of Fourier series. A function f on a comma b is said to be piecewise smooth. So all our functions will be piecewise smooth in this course. So I'll just write the definition. There's something which I had explained earlier, but we don't have to worry about this slide at all, because we will only be talking about piecewise smooth functions. So let me just go to the next slide. So the point is, let f of x be a piecewise smooth function on minus L comma L. So it's like a really nice function, and then the Fourier series of f converges to. So let's see what happens. So the series will, so yeah. So let me make right. So this is my, let's say, minus L. Let's say this is 0 and this is L. So, and let's say my function is something like this, right? Okay, let me just make it here. And here it is, let's say this. Let's say the graph of the function is like this. So at x equal to minus L and L, now notice that this series is a periodic function, right? Because it has, yeah, it has period 2L. So if I replace x by x plus 2L, I get the same value. So the series should have same value at minus L and L, right? And the value of the series is going to be, so I take the average of where is f of x tending to as we come from here, and where f of x is tending to as we come from here. So that's what I've written. So minus L plus, so that is this limit, and L, f of L minus, that is this limit. So at x equal to minus L and L, it converges to this value. And for any x in between, it converges to the limits coming from here and here. the average of the limits. Yeah. So I hope this is clear. So therefore, at every point of continuity of f, the Fourier series converges to f of x. Right. I mean, uh, yeah. So in some sense, in when we look at this statement, we are extending our. So let's say our f was defined like this. So this minus L and this L. So let's say our f is defined like this, right? Now, f is defined on minus L comma L. So will you? The question is, will you say minus L is a point of continuity? So yeah. So I mean, here what we are doing is we are extending small f periodically like this, and so on. So yeah, and therefore when we extend it periodically, this L, all these minus, this L is not a point of continuity because yeah, there's 2L. So maybe I should rewrite this statement as, I should rewrite, therefore at every point x of continuity of f where x belongs to z minus L comma L, the Fourier series converges to f of x. Yeah, but in any case, this sentence is a simple consequence of this statement. So this statement, it's the important thing is you should understand what this statement is saying. Okay, and this is not surprising at all because we have already seen this quite a few times now. So let's go ahead. Okay, this remark is just saying that if we take a nice function f and we can redefine it uh, at finitely many points. So then these ans were defined by integrating f, multiplying f with some function and integrating it. So the integral is not going to change. So the Fourier series, yeah. So the Fourier series of a function is not going to change by changing that function at finitely many points. Okay. So let's go ahead. Okay, let's see an example. Let us find the Fourier series of the piecewise smooth function. So let's make a graph. Let's make the graph of this function. And this example will make everything very clear. So what is happening here? This is from minus 2 to 2. So there's minus 2. And let's say 2 is somewhere here. So it is minus x when x lies between minus 2 and 2. So, okay, so that will be something like this, right? And it's half when x lies between 0 and 2. So half, so this is, let's say this is 2 and this is 1 and this is half. So it's going to be a straight line half. Okay. Right. So we have this function and we are going to try and find the Fourier series of this function. So we compute a0 first. So a0 was, you have to remember the formula. It was 1 upon, here L is equal to 2, right? And a0 was 1 upon 2L. This is 1 upon 2L f of x dx. And you can easily check that this is something. Okay. And if n is greater than or equal to 1, then we can also compute an. That's also going to be a simple computation. Right. And this, okay, so let me omit the computation. So this is going to be the value of ans. And similarly, we can compute the bns. So this is the value of bns. Great. And therefore, therefore the Fourier series of f of x is this thing. So these are the coefficients. All right. And let us compute f of x at discontinuous points. So, uh, so let's see. Let's go back to the picture that I had made. So this is the picture. So minus 2 is a point of discontinuity. So when we tend to minus 2 from here, we get 2. And when we tend to 2 from here, right, we get half. So therefore, the Fourier series f sub f at minus 2 should be equal to half of 2 plus half. So let's check if this is correct. I hope this is okay. That's 5 by 4. That's correct. Okay. So let's look at the other points of discontinuity, right? So 0 is a point of discontinuity. So when we tend to 0 from here, we have 0. And when we tend to 0 from here, we have half. So f sub f of 0 is going to be 1 by 4. And that's it, right? Because over here also, since f sub f is periodic, here also it will be 5 by 4 at 2. And so I hope that is clear, right? Okay. So let's go ahead. So recall, let V be a vector space along with an inner product. For example, L2 minus 1 comma 1 or L2 0 comma 1 with the standard inner products. Great. Suppose we have an orthogonal set phi 1, phi 2 and so on, which has the following property. For every function f, we have a series summation I greater than equal to 1, ai phi I, which converges to f. That is, this thing happens. Then we say that phi 1, phi 2 is a norm basis for V. Note that this is different from the notion of basis, where we need that every vector should be written as a finite linear combination of the basis vectors. So here we are not writing the function as an infinite linear combination. When we say that f is equal to this series, we just mean that this limit tends to 0. This limit written over here, this limit tends to 0. Right? And we, this phi 1, phi 2 and so on, we call this a norm basis. And the coefficients of phi n in the expansion of f are given by a n is equal to f comma phi n divided by phi n comma phi n. This is something which we have seen many times. Okay. In this situation, we loosely write f is equal to n greater than equal to 1, a n phi n. So the theorem on existence of Fourier series for elements in L2 minus 1 comma 1 can be rephrased. The theorem that we just saw. So let me just go back to that theorem. Right? This theorem. Right? This theorem that we saw is going to say that, is telling us in this language, can be rephrased as saying that the set 1 union cos n pi x, so here there should be n greater than equal to 1. And these functions. All these functions is a norm basis for L2 minus 1 comma 1. Right? And notice that these functions are precisely the eigenfunctions to EVP5. And this sort of fits into the earlier, what I had said earlier, a sort of theme which will come again and again. We have a family of differential equations. So here that differential equation is just, we'll only look at this y double prime plus lambda y is equal to 0, where lambda belong to real numbers. And this collection of differential equations will throw up some solutions, and some of those solutions, when we put them together, they will form a norm basis for L2 minus 1 comma 1, or for a certain inner product space. In this case, the inner product space happens to be L2 minus 1 comma 1. Next, we shall use the above to find norm basis for some other vector spaces. Okay, so this theorem we will use as a main theorem, and using this we will uh, find other norm basis for other vector spaces. Okay, we will see that just as in the case of basis, a norm basis need not be unique. Okay, given a vector space, it can have many bases, right? So in the same way, a norm, yeah. Okay. Okay, so let's go ahead. Eigenfunctions of EVP1 as norm base for L201. So here is the claim. So let f be any element of L201. Then we claim that f can be written as a series. F of x is equal to summation n greater than equal to 1 bn sine n pi x by L. So remember what our theorem earlier said. It said that take any f in L2 minus L comma L. Then I can write f as a0 plus summation n greater than equal to 1 an cos n pi x by L plus summation n greater than equal to 1. Can we say orthogonal basis is unique? That's exactly what I just said. No, it is not unique. I mean, we can find many. I mean, if you take a two-dimensional vector space, if you just take R2, I mean, you can take any two, right? This will be an orthogonal basis with the usual inner product. So in the same way, I mean, an orthogonal basis is not going to be unique. And yeah, as Bn. I mean, most of your questions, if you have any, most of these questions will be answered. Just think about what happens in the usual vector space case. Right? So this is our result. This is the result we will assume, right? This is what we just saw. And now using this, we want to show that the statement is a little bit different. You should look at it carefully. If we take f in L2 0L, then I will be able to write f as this thing, right? So let's see how to prove this. So to see this, so here the idea is we first extend f to minus L comma L by defining in an odd way, in this like this, we extend it as an odd function. So we have, right? So our f is a function which is defined in this region. So we extend it to this region, right? So suppose the graph of f was like this. So then we reflect it. Yeah, oh my God, I have made a, yeah, I don't know. Okay, yeah. So we extend f as an odd function to minus L comma L. That's the first thing we do. And we don't care about how to extend it at finitely many points. So we don't care about what happens at 0, right? Okay. So we call the extended function f tilde, right? So f tilde is, let's say, from minus L comma L to R. And now by our earlier theorem, we know that f tilde has this Fourier expansion. And these are the definitions, right? These are the definitions of A0, AN, and Bn. Okay. So now we just have to prove that these numbers are 0. Okay. So how do we prove this? And that's going to be obvious because, yeah. So let's see. Now note that by the way f tilde has been defined, it is an odd function. So, and yeah, so we are integrating. So f tilde is an odd function. So we're integrating an odd function from minus L to L. So the integral is going to be 0. Similarly, these ANs, cos is an even function, f tilde is an odd function. Therefore, their product is an odd function. Therefore, once again, this function is odd, and therefore ANs are 0. Thus A0 is 0. And similarly, yeah, all the ANs are 0. So this proves that f tilde looks like this, right? But now we just restrict this to f. F tilde, by construction, f tilde restricted to 0L is f, right? So if f tilde looks like this, then f also looks like this. Thus we get the required expansion, right? So therefore we have proved that the eigenfunctions of EVP1, eigenvalue problem 1, form a norm basis for L201. Can we shift it by A0 so that there will be no continuity at 0? There will be no discontinuity at 0. I'm not sure I understand your question. Let me think. No, that's not possible, right? I mean, like, I could take some function which looks like this. So let's say minus L to L, right? Now, the series of this function, there's only one point of discontinuity. Okay, there are 2 points of discontinuity, this and this. But let's just focus at the, I'm sorry, there are 2 points of this, these three, these 3 points of discontinuity are there. So let's just focus at 0, right? So now when you write the series is, and you make the graph of the series, at points of continuity, the series will look like this, right? So no matter where you define, I mean, I don't know, no matter where you define f, your 0 is never going to be a point of continuity. You can redefine your f of 0 so that the series is equal to f of 0 if you like. I don't know, does that answer your question? Yeah, you just have to pause and think about it. Yeah. So I mean, you can, if you start with the f, you can cook up its Fourier series. Let's call it f sub f. And the Fourier series is going to have some values. So you can redefine your f at some finitely many points of discontinuity so that it becomes equal to the Fourier series. But that's the best you can do. I mean, yeah. It's kind of too much to say that I will redefine my f at one point and then so that the Fourier series becomes continuous or something. Okay, anyway, I think I'm not, I don't really understand your question, but I think the example that I made, if you think about it, if you think about it, that'll answer your question. Okay. So the main point is, so using our theorem on existence of Fourier series on L2 minus 1 comma 1, on this L2, using the above theorem which I stated for Fourier series on L2 minus 1 comma 1, we have now proved this theorem. That is the main point of what we did right now. Okay, so let's go ahead. Eigenfunctions of EVP2 as norm basis of L201, right? So now what do here we are going to give another orthogonal basis. So what do we, yeah. So let's see. So let f be a function on 0L. Then we claim that f can be written as a series. F of x is equal to A0 and like this, right? So this means that even one, so what in the previous slides we saw that sine n pi x by L. This is an orthogonal basis for L201. Now this is saying that A0, comma, I'm sorry, not A0, 1. Okay, let me just write it as cos n pi x by n greater than equal to 0 is an orthogonal basis for L201, right? So yeah, for the same inner product space, we have produced two different ones. So let's see how to do this. This is very similar. So this time, instead of extending it as an odd function, we will extend it as an even function. So let's say our L is defined in this region first. So let's say, once again, let's take the same example. It's something like this. So we just reflect it. So it will look something like this. And this is our f tilde. So f tilde is defined on minus L comma L. Okay. And now f tilde has a Fourier expansion where these are the definitions of the coefficients. So the same thing applies, right? So this time we need to show that all the bn's are 0. Okay, there should be been a bracket here. This time we want to show that all the bn's are 0, but that's clear because f tilde is extended as an even function and sine is odd. So this function is odd and we are integrating from minus L to L. So which means that bn is 0. right? Okay, there is a typo here. Sorry. Okay. Okay. Uh, so then we can do the same thing. Eigenfunctions of EVP3 as norm basis for L201, right? We can create another one, another, right? So I will, so EVP3, so let me see, right? Right. So once again, it's a similar construction. So yeah, and EVP3 and EVP4. So I'll skip EVP3 and EVP4. The point is that when we solve our uh, when we solve our partial differential equations, depending on the boundary conditions, we will have to, yeah, okay, we will have to choose a particular, okay, I think it will be explained better when I reach there. So let me omit that. So EVP3 and EVP4, the details are given. They are very easy as the earlier ones. So if you're interested, you can take a look at it. But from an exam point of view, this is not going to come in the exam. So let me just skip it. So let's come to this slide. So what is the point of all this? Okay, so we have seen 5 theorems now. Each of these says that there is a certain norm-linear space V, and that eigenfunctions of a certain problem form a norm basis for V. Okay. Also note that that the 4 of the above theorems are easy consequences of the main one, and the main theorem, which we of course is going to be a deep theorem, is that we have is a theorem we said about L2 minus 1 comma 1, that uh, 1 and cos n pi x by L and sine n pi x by L, right? These, right, form a norm basis for L2 minus 1 comma 1. Okay, so what? What is so interesting about this? Who cares? So the power of these theorems will be revealed when we use them to solve PDEs. And so recall, so the PDE we saw in the first lecture is this, right? In my first lecture, I had mentioned this PDE. I had thrown it to all of you as a challenge. If you want, you can try this, right? So this PDE was ut is equal to k square uxx, u0 t is equal to 0, ult is equal to 0, ux0 is equal to x times L minus x. So depending on the form of this, yeah. So depending on these two, so okay. So you will you will have to decide which. So you will usually write this as a series, right? You will write this as a series, and what kind of series you have to choose, that will be decided by these two. So if these two are in this form, then you will simply write this thing as a series using your sine n pi x. Anyway, we will come to this. So yeah. So to solve this, we will use the Fourier expansion in terms of EVP1. This will be done in the coming lectures, right? So because when your boundary conditions are in this form, then so to solve this, we will use the Fourier expansion. To solve this, we will use the Fourier expansion of x into L minus x in terms of EVP1. So how do you decide, which EVP to choose? So, in terms of, I should have written in terms of eigenfunctions of EVP1, in terms of the eigenfunctions appearing in EVP1. So, how do you decide whether you should choose 1, 2, 3, or 4? And that is going to be based on the form of these two conditions. Okay. Okay, so this is a silly observation, and maybe we will start with it next time. So, I will stop here. I will end today's lecture here. If there are any questions, I can take them. Well, so Niklesh, the point is you can extend the function in whatever way you want. Yeah, but I mean, you what you really want is you want to prove that such and such thing is a norm basis. So, I mean, if you extend it in some random way, you will not be able to prove your theorem. That's it. I hope that answers your question. Is the same idea used for Legendre or Bessel functions while solving PDEs? Uh, yes, that is correct. So for certain kinds of PDs, yeah. So I will. So there's this question: is the same idea used for Legendre or Bessel functions while solving PDs? So I don't quite understand what your question is, but I will make a comment on this maybe in the last lecture. I mean, I have a guess as to what your question is, but I don't want to. I mean, I cannot be sure what is in your mind. So yeah. So I suggest you be a little bit patient. Yeah, that's it. So this is the heat equation. This is the heat equation, right? So yeah, if you want to solve the wave equation in, yeah, I don't remember the exact equation now. I'll yeah. But anyway, so that's where uh oh, so for certain kinds of, yeah, maybe I can say right now. So to solve these kinds of differential equations, we will do this. We will take this thing and write its Fourier expansion in terms of eigenfunctions for EVP1. But there will be other kinds of differential equations where there will be some function which appears in the boundary, and we will have to write the expansion of those functions in terms of Legendre polynomials or in terms of Bessel functions. Yeah, I think, yeah, this is what I wanted to say. So I have answered. I have answered to what I thought your question was, to my guess of what your question was. Any other questions? Okay. So I don't think I have uploaded a chapter called wave equation in two variables uh, on the course webpage. So if you look at that, I don't know, maybe I can check. Okay. Yeah, okay, I don't know. Yeah, Pranava, if you just come to the last lecture, I think your question will be answered very precisely. Are there any other questions? If there are no other questions, then we can end. I'll just wait for a few more minutes. So the exam was very easy. So uh, 651 students wrote the exam and minus 194. So that's a pretty big number. So these many students have already scored 15 out of 26. So these many students have already passed the course. So they don't need to give the NSEM. So even if they don't give the NSEM, they will pass the course. I don't know the mean score yet, but it will be quite high, I suppose. So I think some uh, 32 or 33 people have gotten 26 out of 26. Okay, so if there are no other questions, I will end today's class. So I suppose that many of you will be at home and maybe enjoying the holiday season. So yeah, enjoy yourself. That's all that I have to say to you. Yeah, bye.